And I Great. Okay, hi everyone. Welcome to another review session. How are we feeling this week so far? Okay, ish, mid. Okay, well, we are midweek, so I guess that's valid. I think there's, in terms of announcements, no quiz this week, quiz next week, exam the week after that. So you have 2 weeks until your first exam. In terms of what I will do for your exams, we will have a little bit extended office hour that Wednesday before. So if you're in Bengali, that will be like your last little bit is the Wednesday before. We'll have like an hour and a half session before the Thursday exam. And then I'll also do an Zoom review Tuesday night. And then you can ask some questions there as well. So it'll be Tuesday and Wednesday. And then you'll have your exam Thursday or Friday. Any questions on that? Yeah.
In class.
It's in class. Yep. For your exam, it's in class. All of your quizzes are online, but your exam is in class. Yep. I don't know yet. I'll figure that out. I'll let you know next week. I need to see what my lab schedule looks like coming up. I don't know, there's been someone in here right before us, so maybe it'll go 5:30 to 7 instead of earlier. But we'll do it a little bit longer. I can stay a little bit longer that day. Any other questions? Okay, and then I had a couple requests for net ionic equations and limiting reactants. Does that sound okay to go over? Sweet. Alrighty. So we will start with net ionic equations. Yeah, absolutely. Yeah, we'll do these two things first and then we'll allow time for that. Alrighty, so when we talk about net ionic equations, can someone tell me what a net ionic equation is? Yeah.
It's the equation that's up to
Perfect, right? So you have your leftover chemical reaction. What do we call the things that we cancel out? Spectator ions, right? After spectator ions are canceled. Right, so for a net ionic equation, this is this is showing you what chemistry is actually happening, right? You can have your full balanced chemical equation, you can have your reactants, you can have your products, but some of your reactants are just kind of going to hang out and some of your products are just kind of going to hang out. What the net ionic equation is showing you is what chemistry is actually happening. Okay, so one thing that we tend to look at is an acid-base reaction. So if we have HCl and NaOH, what is HCl? That's hydrogen chloride, hydrochloric acid, right? So that's an acid. Is it a strong or weak acid? It's a strong acid. What about NaOH? That's a strong base. Perfect. What happens to strong acids and strong bases in solution? They're going to dissociate. So that's going to split up into H plus and Cl minus, and Na plus and OH minus. Now, just in our reaction, what is HCl and NaOH? When they go into solution, what are they going to form? Water and a salt, right? So we have H2O, and that comes from HOH. And what's our salt that gets formed? Sodium chloride. And that comes from your Cl and your NaOH. Right, so you switch partners. This happens with any sort of double displacement, we call it, reaction. So if you have, just as an example, AB plus CD, it'll end up with CB plus AD. right? That's the format it's going to look at. Your metals are going to switch the anion that it is associated with. So going back to our HCl and NaOH, those are now in solution. What phase is water? Liquid. What can we do with liquids? Nothing, right? So that's going to stay as H2O. What happens to NaCl? That's also aqueous. So what is that going to do? It will also dissociate. Aqueous. Yep. Yep. This would be aqueous. Both of these would be aqueous on this side too. Okay, so if we're going to write our net ionic equation, what are we canceling out? Good, our sodium and chloride. They're not doing anything, right? You put them into solution, you have a HCl beaker and you have an NaOH beaker, you mix them together, they stay as their ions the whole time, right? You just create more water around it. So overall, we're going to end up with H plus and OH minus forms H2O. And that's really all the chemistry that's happening with an acid-base reaction. Go ahead.
Here's how this works.
Mhm.
Because they did split up, so why are, I don't like you say that no chemical reaction happened between Cl and Na, like Cl minus and Na plus.
Mhm.
And no, you're saying no chemical reaction, but they changed partners, so I like, how is there no chemical reaction happening?
So it's not necessary, it's almost as, you can think about it as they formed and then they immediately split up again, right? They are already in this pocket. So when HCl is aqueous, you have your H plus ion and you have your Cl minus ion, and you have water molecules that are surrounding both of these in like a bubble, right? So the oxygen is going to be pointing towards your H plus, and then your hydrogens are pointing towards your chlorine ion. So they create like this bubble around the ion. So you already have water molecules surrounding them. So when you put that in solution with sodium chloride or with NaOH, the water molecules, the H plus and then the OH minus ions have a similar thing happening. So these will pair up and create more water. And sodium itself is going to keep its bubble around it. And they're just going to stay in their little bubble. So no chemical reaction happens because they never really form the salt to then split. They just kind of stay as the ion itself.
So, NaCl never forms in again?
Really, it doesn't never form. It would only form if you boiled off the water,
Oh, okay.
right? Because you're removing that bubble that's surrounding them, and then they're able to come to go close enough together.
NaCl is never actually manifesting, we're just doing it to balance out the equation?
Yes. Yep.
Oh, okay.
Yep. And so that's why the net ionic equation is showing you what's actually happening, right? We don't care about sodium chloride because it's not actually doing anything.
And we know this because it's like, they're aqueous on both sides?
Yes. Yep.
Okay.
And the reason that NaCl is spectator ion is in like split up, it's because it's covalent by soluble, right?
So we can split it up into, what do we call those? The Na plus and the Cl minus. People can help them out. What are those called? Na plus and Cl minus. They're ions, right? So if you have two ions, what bond is formed between them? An ionic bond, right? An ionic means you have two bonds. Oh, that's unfortunate. You have a bond that is formed between fully charged atoms, okay?
the HCl and the OH would dissociate, do you even know, do you know that because it's strong acid and strong base, or do you know that just because of the solubility?
You know that because there are strong acids and strong bases, the solubility chart supports the reason that they are strong acids and strong bases. But your 6 strong acids and 6 strong bases will always fully dissociate.
So if they're weak, they won't fully.
Right, if they're weak, they're not gonna fully dissociate, and so that brings up the one homework question. So if you have this reaction. Someone identify what we have here. We have hydrogen phosphate. Does anyone know another name for that? If you see an H at the front, what are we gonna think that's gonna be? That's probably gonna be an acid, right? Is that one of our, that's phosphoric acid, awesome. Is it a strong or weak acid? It is a weak acid. The only strong acid that is diprotic is hydrosulfuric acid, and that's H2SO4. Or sulfuric acid.
And we can post things as strong acid if it's on that chart thing.
Yep.
And there's only 6 like combinations, right? It's like between the like 6 ionic bonds or whatever.
There's only 6 strong acids and there's only 6 strong bases.
Okay, and acids are when there's 2 like compounds.
The acid will always have a hydrogen in the front.
Are we gonna have access to the common acid basis chart?
I think usually it'll tell you it's strong or weak in the question, but I recommend knowing your 6 strong acids and 6 strong bases. Is there another question? Okay, yep, I recommend knowing those. For your, do we know what our 6 strong acids and 6 strong bases are? Okay, we'll do that first. So we're gonna move this down. So you have your strong acids. Can anyone name a couple of them? Yep, we have hydrochloric, I think that's the one you're looking for, right? Yep. Hydrobromic. Yep, perchloric is the HClO4, perfect. There's one more. Yep. So we have HCl, HBr, HI, HNO3, HClO4, and H2SO4. I personally have not come up with a way to like visually see this on the periodic table, bless you. But you do have all of your that group 17 right there. Cl, Br, and I are all on the group 17. Except for fluorine. Fluorine is not a strong acid. And then you just gotta remember the other 3. I don't really have a trick for that one. If you come up with a trick, let me know. Strong bases. Do we know what our strong bases are? Yep, sodium hydroxide, lithium hydroxide, potassium hydroxide. What else? What else? Magnesium is not one. The other 2 are going to be strontium hydroxide and barium hydroxide. So that's from your chart. how they determined that those were strong acid or strong bases, I don't know. But I wrote it like this because if you look at your periodic table, you have lithium, sodium, potassium, go on over to calcium, strontium, and barium. So you have the 6 right there in that little zigzag. And so that's how I can always visually remember my 6 strong bases because they're all connected with each other. You have 3 monoprotic and 3 diprotic strong bases. So if you just start with the very top, you can move down and across to your periodic table. In terms of your strong acids, right, you have chlorine, bromine, and iodine. And then you have nitrogen, sulfur, another chlorine. Those are all kind of there, and all of those need oxygen. They surround oxygen, right? That can kind of be your visual if you think about that one. What does it have? And
Just has the lithium, sodium.
those are 3 other ones. Yeah, I don't know. Maybe they won't ask you anything or too much about the other ones, but lithium, sodium, and potassium are like the most common. Yep. It's still an ionic bond, and ionic bonds in solution will completely dissociate. Okay, any questions on your strong acids and strong bases? Awesome. So going back to our question, we have H3PO4 and we have calcium hydroxide. So what do we have with phosphoric acid? We have a weak acid and we have a strong base. What is going to be the compounds that are formed? Still always water, right? Whenever you have an acid-base reaction, no matter if it's a strong acid, strong base, weak acid, strong base, strong acid, weak base, or weak acid, weak base, water will always be formed. What else gets formed? Calcium phosphate. Can anyone balance that for me? It's yeah, calcium hydroxide with the 2. Yep. I guess, can you balance the calcium phosphate to make that a neutral compound? We need 3 calcium and 2 phosphates. Does everyone know why I need 3 calciums and 2 phosphates? Good. So there's 3 hydrogens right here, and that's to balance out the -3 charge of your phosphate. The 2 from your hydroxide has a -1, so you have -2 to balance out the +2 of your calcium. So you need to switch those there. Yes. So this is just looking at the question, you can always say that this is a double displacement, so you're always going to switch your partners. And a weak acid will still dissociate a little bit. It's not going to dissociate fully like a strong acid, but it will dissociate a little bit. Alrighty, and then how are we going to balance our equation? Mhm. And I think that's balanced. Anyone have any objections? I think that's correct. Okay. So now we need to write our complete ionic equation. We just said that H3PO4 is a weak acid. Is that going to completely dissociate? No. So what do we do with our ionic equation, right? Our complete ionic equation with a weak acid? We keep it together, right? This is just like saying this is a covalent compound, right? It's one unit. So this is H3PO4 aqueous. What about calcium hydroxide? This will dissociate. So this is going to be 3 calcium 2 plus and 3 OH. Yep, sorry.
The phosphoric acid didn't dissociate from the meat.
If we were, so when you start working with acids and bases, your H3PO4 will actually look like an equilibrium, and it'll be H plus H2P. It'll look like that.
Is that also what acid? Is that also acid?
So then this now also becomes an acid. So then you can write it as H2PO4, and this becomes an equilibrium of H and HPO4. And then this becomes an acid, and you can write that as HPO4 2 minus as an equilibrium. And that is where you see this allowed to make a compound with the calcium. So that's where that comes from. It'll be the arrow, yeah. Okay, and then what do we do with our water? We keep this the same. And what do we do with our calcium phosphate? That can dissociate. I lied to you. This is actually a solid. Yes, yep. I just didn't look at my chart until just now. So what do we do with the calcium phosphate? We leave it. You can look at your solubility chart. Yep, so you would look at PO4 3 minus, you would look for that anion first and then see if it's either soluble or insoluble, and then if there's any exceptions. Yep.
So you said the strong bases and strong acid chart might be on it. And then your table will be on it.
Mhm.
Balance and ions will be on it.
Yes.
Is the solubility chart.
Yes. Yep. Yes. Mm-hmm. For this purpose, you can write it as 6, because you do get 2 of that. I'm just showing you that it stays the same as you move it down. Technically, you should write it as 6 because this splits up into 2 hydroxide ions. So we could also write this as 6OH. That's technically the correct way to do that.
Okay, those accepted.
The 6OH minus is more correct. Yeah. Alrighty, so can we cancel anything out? Nope. So this actually becomes your net ionic equation. No, I'm just making it look prettier.
We break up and see spectator ions twice to make sure that a combination, we don't see anything like Ca3PO4, we don't see that on the temperature.
Yeah, yep. So whenever you're predicting your products, if they give you, right, I just gave you the first half of the reactants. They're just giving you reactants and you're asked to predict the products, always pull up your solubility chart next to it. Insoluble. Yeah, if it's insoluble, then that means it's a solid.
What?
Sorry, go ahead.
Oh, I didn't raise my hand. What?
I was gonna say, if it's not, like, if it's on the insoluble, could it be like a gas or a liquid instead?
Technically, yes, but 99% of the time it'll be a solid.
So what happens to, on one of mine works, it had, HCIO2 instead of HCIO4. Or L, I'm sorry,
Mhm.
HClO2 instead of HClO4, so
Mhm.
that's not on the, chart.
Mhm.
And so how did, cause it's split apart on one side and then not on the other.
Yep. So what they did is they kind of combined, right? So HClO2 is not on your chart, which means it's a weak acid, right? If it's not on that strong acid chart, it's a weak acid. So they took what you did in like this first part where we broke it up into this, and we said that it gives a hydrogen plus ion. It says it technically does that. So it does dissociate a little bit, but it doesn't dissociate completely. So that's why it's broken up on the product side.
Why put it on the reactant side? And not the- It's really weird.
Show me after when we're done, and I'll try and explain that a little bit, or I'll look at it again a little closer.
Thank you.
Yep. But does that make sense in terms of
Yes,
everything
that
else?
makes
Yeah.
sense. So if it's not the strong acid chart, that's.
Yes. Yep.
And if somebody's on the base.
Yes. Yep. If it's not one of the 6 strong acids or strong bases, you can call it weak. Say it again. It is aqueous. Thank you. Anything else? Just help net ionic equations a little bit. On, I think it was week 3 practice problems, I have 3 of these written out for you, and then you have to predict the products, write the balance reaction and everything, so you can have a couple more practice problems there. And if you look up net ionic equation practice problems on the internet, a good couple worksheets pop up as well, if you need more practice with that. Alrighty, anything else before we move on? Sweet. Okay, so now we'll move into limiting reactants. And the biggest thing I want you to know with limiting reagents or limiting reactants is that whenever you're given a question that gives you information about the concentration of both reactants, right? Both reactants. Concentrations, masses, volumes, something where you have information for both the reaction, for both reactants in your question, and no information about products. It's going to be a limiting reagent question. They can ask you questions where they say, so much of this reactant is produced, right? How much reactant or so much of this product was produced, how much reactant was used, something like that. That's still a limiting reactant question, but you would be given information about both reactants in that case when you're asking for it. Right? You have information about everything on the left-hand side of your chemical equation, but not a lot about your right-hand side. So if we just have a general reaction, we could say yep. Right, we have given 2 moles of A and 3 moles of B. How many moles of C are formed? So when we're reading this question, do we see how we have information about a concentration or a value for both A and B, but nothing about our products? Right, so this is going to point us into saying, okay, I do have a limiting reagent question because I know a lot about my left-hand side, but not a lot about my right-hand side. How are we going to figure this question out? How are we going to determine how many moles are formed?
We can determine the ratio.
Awesome. Do we know what that ratio is called? Right, your stoichiometric ratio. That's the coefficients in front of your products and reactants. That's the stoichiometric ratio that you're using. So for 2 moles of A, what's our stoichiometric ratio? Two to 1 of what? Good. So there's 2 ways that you can solve for limiting reactant. You can do it one way where you say, I have 2 moles of A for every 1 mole of B. Or you can say, I have 2 moles of A, and for every 2 moles of A, I have 3 moles of C. How many moles of B do you get? You get 1 mole B. How many moles of C do you get? You get 3 moles of C. Question, yep. No, so this is our chemical reaction is 2A plus B goes to 3C plus D. I'm telling you that you're starting off with 2 moles of A and 3 moles of B in your reaction. And so then you're determining how much of C and D get produced based off of the chemical reaction.
It would be just like.
I think there's a question, like not in the formula, but in the question where it says 3 moles of B.
Yes, but your chemical reaction the stoichiometric ratio is 2 to 1 for your products or for your reactants. Right, I could have just said you have 15 grams of A and 6 grams of B. Right, that's going to be the same thing here, but I'm just giving you moles, right? You would still be using that 2 to 1 stoichiometric ratio after you convert it to moles first. I will do a real problem, maybe it'll make sense there. Okay, so you get 1 mole of B and 3 moles of C. If you use it in this top method, you have to ask the question of, do I have 1 mole of B? Right, you want to ask, do I have 1 mole of B? Do you have 1 mole of B? Yes. When you do it from the reactants to the products, you're saying, I'm producing 3 moles of C. We have not found what our limiting reagent question, or what our limiting reagent is. We have to do this as well for the moles of B. So we're given 3 moles of B, and you can do it the top way where you compare to your other reactant. And you can say that for every 1 mole of B, you need 2 moles of A. How many moles of A do we need then? You need 6 moles of A. Or you can say for every 3 moles of B, the ratio is 1 mole of B to 3 moles of C. So how many moles of C are you going to produce? You're going to produce 9 moles of C. So we're going to ask ourselves the same question. Do I have 6 moles of A? No. If you say no, that's now your limiting reagent. When we look at C, we're going to say I'm producing 9 moles of C. So if I used up all of B, I would produce 9. If I used up all of A, I would produce 3. Which one's our limiting reagent? A, because it's producing less than C. So in this case, the 3 moles of C is your limiting, or the 3 moles of C is the least amount of product you can produce. So that means that A is your limiting reactant. In both cases, how you're doing this, you still get that A is the limiting reagent.
Why did you see humans of B? Why does it not basically match?
The values you're given in the question do not have to match the stoichiometric ratio of your chemical reaction. Any other questions? Okay, let's do an actual problem. And maybe that'll clear up the mole question. Alrighty, so for this one, we're gonna determine the limiting reagent. We know that 6 grams of Fe2O3 is reacting with 3 grams of carbon monoxide. What's the first thing we need to do? That's a lie. What's the first thing we have to do? You want to make sure that your equation is balanced. In this case, it is. I gave it to you balanced, but the first thing you always want to do is check to make sure that your equation is balanced. Trick question. What's the second thing we do? Now we can convert grams to moles. So here's your periodic table. Do we get a molecular weight for iron oxide? Perfect. So we have 6 grams of iron oxide. For every 1 mole of iron oxide, we have 159.7 grams. What do we do once we have grams to moles? Perfect. We need to use our stoichiometric ratio. Doesn't matter which one you use. I prefer to convert to my products because I like to see how much is produced. That just is easier in my head. It does not matter what product you convert to. I'm going to use iron. So for every 1 mole of iron oxide, there's 2 moles of iron that can be produced. You can get 0.075 moles of iron. And then we're going to do the same thing for carbon monoxide. So we have 3 grams of carbon monoxide. For every 1 mole of carbon monoxide, you have 28.01 grams. What's our stoichiometric ratio for this one? 2 to 3. You want to use the same product when you're comparing your 2 reactants. So even though it doesn't matter which one you pick, you want to make sure that you use the same one. So every 3 moles of carbon monoxide, you get 2 moles of iron. And we get 0.071 moles of iron. So which one is our limiting reagent? The carbon monoxide is going to be our limiting reagent. So we want to compare how many moles of iron are being produced. So what we're doing when we set up these 2 equations is we're saying, okay, if all 6 grams of my iron oxide is being used up, then I'm gonna produce 0.071 or 0.075 moles of iron. If all of my carbon monoxide gets used up, I'm producing 0.071 moles of iron. I have to pick the 0.71 moles of iron as my limiting reagent, or that's the least amount that I can produce because I don't have enough of my carbon monoxide to make 0.075. I can only make 0.071. Yep.
Does it still work if you put the ratio of oxygen on top of that? Does it matter what we put on top?
For like your product. Yep. So if you did carbon dioxide, you can prove that to yourself and you would still get that carbon monoxide was the limiting reagent. Does that make sense? Right? And that's a good check, right? You can always check it to make sure that that works out the same way. Mhm.
Do this process of converting full grams or whatever the process name.
Mhm.
And see whichever one produces the least amount, and that's our.
Yes.
Oh, that makes sense.
Yep. That just determines your limiting reagent. Right. You can then go further, right? You can say how many grams of iron is produced. You can then take your limiting reagent number of moles of iron and convert that to grams using its molar mass. You can convert that to atoms, right? If you have moles of iron, you can convert that to atoms of iron using Avogadro's number. And then you can determine how much is left over of your excess reagent as well.
Yeah, so what if they ask us to determine like how much of the excess reagent that we actually?
Yep, we can try and. Actually, we can just do it with this one.
Use the ratio of the 0.071 moles, like compare that to the ratio.
No. So if you want to find how much excess reagent is left over, which one's the one in excess? Fe2FO, right? This is your excess. If you're looking for your excess reagent, you're now going to do like that top portion that we first looked at. We're going to compare the ratios and how much we have between our two reactants. So we're going to set it up the same way where we have 3 grams of carbon monoxide because this is still getting all used up. All of our carbon monoxide is going to be used up at the very end. So every 1 mole of carbon monoxide, we have 28.01 grams. But now we're going to compare reactant to reactant. And so what's our stoichiometric ratio for carbon monoxide to iron oxide? 3:1. For every 1 mole, of iron oxide, we need 3 moles of carbon monoxide. So this means that we use 0.0375 moles of iron oxide. Yep.
If we converted that like iron oxide into grams, it would be less than the 6 grams we're given.
Yep. So let's do that as well. Bless you. So we said that 1 mole of iron oxide was 159.7 grams. And this ends up to be 5.70 grams of iron oxide. Yes.
What are they asking?
How much excess reagent is left over?
Oh.
For this blue portion?
Yeah, so like 0.0375, what's the question asking for, and then what's the question asking for?
Yep. So we're still asking right here for how much excess reagent remains. So we stopped at moles and then we used that moles to convert to grams. You could have just put that second set of parentheses just right next to that above. Yep.
Is that 0.0375, is that how much FP2O3 was used and how much was left over?
That's how much was used, which means that we used 5.70 grams, because in order to use all 3 grams of carbon monoxide, we're going to use up 5.7. So have we answered our question yet? No. What do we, yep, I heard that. Perfect, right? You need to subtract your 6 grams that you had from your 5.70. So how much excess reagent remains? Point 3 grams of iron oxide remains.
So does that mean if, like, in actual reaction, if we wanted to get like no leftover, then we just use 5.77 plus 6?
Yep, right. If you wanted to be completely used up all of your reactants, then you would either need to add more carbon monoxide or you would just use 5.7 grams instead. Yep, great question. Yep. Hmm. For, I just picked a product. You're just trying to find whatever the limiting reagent was, so it doesn't matter what you convert to, you just need to compare the same product in both cases. You could have picked carbon dioxide and you would still get that your carbon monoxide was the limiting reagent.
What did you say was the question of
For the blue part, we're just asking for how much excess reagent remains. So we know that carbon monoxide is our limiting reagent, which means that we have more of our iron oxide. Not all of that iron oxide is going to get used up. So we want to know how much is left over once the reaction is gone to completion. Yes. Nope, it's just one question. You could have, instead of stopping at moles of the iron oxide, right here, right? We could have just put this portion right next to it. Yep. Mm-hmm.
I think we did this on Monday in chemistry, but it was like questions like upon the completion of the reaction, so, there's like the combustion ones and then like how much was consumed and questions like that, but,
Mhm. So that's just versions of what we're doing right here as well, right? If you have a combustion reaction, right, in this case, you could say questions like, yes, for combustion, that will always be the case. Yep. Okay, so this is kind of all the questions you can, or some, there's probably more that you can ask from this, but these are like the 3 popular questions that you can ask from a limiting reagent question. So we have, what is a limiting reagent, right? Just tell me what is in the least amount. How much of a product is produced? In this case, we're asking for CO2. And then we're looking for how much excess reagent remains. Okay, we don't need to go through this right now. I will do this when I get home and then post it along with the notes and the in the review video. But these are 3 that you can practice on your own. What's the first thing we need to do though? Right, balance your chemical reaction. When you're looking for the limiting reagent, if you're going to use a product, which one should you use? Sure.
The one.
Right, I'm asking you later on for carbon dioxide. So when you're trying to find your limiting reagent, if you're comparing to things that are produced, pick the carbon dioxide, because then you already know how many moles of that is being produced. You don't need to go back and do your steps again. To find, right, if you solve for water, you don't need to do it again for carbon dioxide.
So then if we, just like the previous question, if we get the 2 amounts that were produced, and in this case, we're asking for how much CO2 we basically left number for that.
Yep, and then we'll say. Right, so then you have to pick a grams one. Okay, so you can try this on your own. I just wanted to leave a couple minutes for the quiz question. If someone wants to tell me what that was. They said it was the last question. Someone have it that I can look at? I don't think I can pull that up that fast. Thank you. Thanks for coming. Yeah. How do what? Ooh, I would have to look at my howdy.
Yeah, you go to conditions.
Yeah, it's true. I can explain that.
Yeah.
So if you can do the cross section with a square with like 2.5 minutes.
Okay.
And then it's like the lane was like 1.4
Okay.
then it gave you the NP with like yeah, I don't know who like but it's funny.
Square compound, 1.5, and then the, it was. It's the volume, this, and then it goes out.
So it was a copper link, so the cross sectional link was 2.5. Yeah.
Okay.
And then it gave the density, and then it also gave us the copper.
If you have it, that would be, yeah. Yeah, whenever there's a clicker question, I'm like, okay, here we go, stand up. Great. Okay, let's see.
Well, I don't get it easily. It's not, yeah, it's not. Well, I thought I released it somewhere. You just go and go to your grades.
It's gonna be like.
So,
You're gonna be like negative.
yeah, that's
Oh,
fine.
you know, I did see it, and I forgot.
Was it right on the nanometers and micrometers?
I think it changes per student, so I'll just use what she has here.
Okay.
Leave it there. Yeah, and then that way I can just make sure I'm doing it right if I get the correct answer it's showing you, so. Okay, and then yours was. Okay, so for this question, right, it's saying copper wires and computer circuits are approximately 20 nanometers wide and have a square cross section. So the thing you need to know there is that squares are all the same on the same side, so your width and height are gonna be the same. So that's why the 20 is on both the bottom and the side. Yep. It's the last quiz question, number 10, I think, on the quiz, quiz number 1.
Oh.
Yep. And then, so they're asking for how many copper atoms are in a 1.7 millimeter. Just make sure that this is all the same, so I get the correct answer of such a wire, and you're given the density of copper and the atomic weight of copper. So what do we know about density in the units that's given? What is its mass over what? Volume. Can we get a volume from that copper wire that we're given? Yes, we can, right? We have a height, a width, and a length. So your volume is going to be length times width times height. But you need to convert your 20 nanometers and your 20 nanometers and your 1.7 millimeters to centimeters because your density is in centimeters. So if we have 20 nanometers for every one, I always convert to meters first. So 1 meter is going to be 1 times 10 to the 9th nanometers. And then for every 1 meter, it's 1 times 10 to the negative 3 centimeters. This is 2 times 10 to the negative 11 centimeters. No, hold on, I did my exponents. Okay. Oh, because this is not 3. So I'm sorry, this is 2 times 10 to the negative 6 centimeters. Nano is times 10 to the negative 9. So that's where I just changed my nano to times 10 to the negative 9. And then for 1.7 times 10 to the negative 3 meters, right? That's millimeters. Then for every 1 centimeter, it's 1 times 10 to the negative 2 meters. Just ignore this. Yeah, just ignore that. My math is not working in my calculator. That one does. So and then this. This is 0.1 centimeters. So this is your width and height. This is your length. So now you can use your converted volume units to get to a volume. So volume will be 0.1 times 2 times 10 to the negative 6 times 2 times 10 to the negative 6. This is 4 times 10 to the negative 13 centimeters cubed. Okay, that gets you a volume. We're given a density, so now that we can say that density is equal to mass over volume. And in order to get to how many copper atoms are in this unit, we need to get to grams to moles to atoms. So given 8.96 grams per centimeters cubed, we can multiply by our volume, which we just found. And we can get a mass of 3.584 times 10 to the negative 12 grams. We can then use that mass. We convert to moles of copper using its molar mass. So for every 1 mole of copper, we get 63.546 grams of copper. And then how do we get to atoms of copper? Then we can use Avogadro's number. So for every 1 mole of copper, we have 6.02 times 10 to the 23 atoms. They're mostly for the units you're covering at the time. Yep. So then you get 3.395 times 10 to the 10th. This number is slightly different from what the correct answer says here, but the general setup is correct. All right, so what we did is we converted our units to centimeters cubed because that's what our density volume is in. I might have screwed that up there, so just bear with me. Right, but we need to convert our units to centimeters cubed. We then used our centimeters cubed of our volume of our copper wire to get a volume using length times width times height. We then used our density in order to get the mass of copper wire of copper atoms within that volume that we're using. And then we use that mass and then its molar mass of copper and then the Avogadro's number in order to get to the number of atoms for that copper. Does that help clear it up a little bit? Just go back and check your conversions because I might have screwed that up there, but it's 6:40 on Wednesday, so. Thank you. Yep. Is there any other questions with this one? This is probably one of the harder questions you would see on an exam. Where you have to use a couple units, you have to do a couple conversions, right? You kind of have to have a roadmap and for the short answer questions. Yep. There's usually like 3 or 4 short answer questions. And so this would be like a short answer question.
Paper or?
Yep.
Okay, so did you get partial credit?
Mhm.
Is that?
Yep, there's usually gonna be multiple choice and short answer, so you'll have like probably 10 to 15 multiple choice. And then 3 to 4 short answer, or I guess maybe 4 to 6 short answer. Couple of them will be like fill in the blank or circle an answer choice, and then a couple of them, 3 to 4 of them will be like these longer problems. Yeah. Thank you.
Like, where is that? That on clinics?
What class are you in?
I'm in 107 with, Dr.
With Dr. Altimos? Yeah, so if you go to Canvas. Thank you. So if you're in Dr. Altimos's class, if you scroll down to the office hours page and click on that, and then scroll it down here, I post, it's the button next to syllabus. Yep, so you click on that and scroll down a little bit to 107 IA sessions. I have video notes and then extra problems in the answers for the past 3 weeks.
So this was the beginning of the quiz.
Mhm.
First, just for this one, I thought that pure substance is only whenever it was just like nickel or just sulfur, not like when they're together. Is that? like,
So,
totally wrong?
you're not totally wrong. When we look at this, nickel sulfide here is going to be a compound.
Okay.
So when it's compounded together and you
Mhm.
have only a sample of that compound, it's still a pure substance. So that's like
Oh.
saying you have water, you
Yeah.
just have water. Is that
Okay.
gonna be a homogeneous mixture or a pure sample?
Pure sample.
Pure sample,
But if it was this and water,
then
then,
it's a homogeneous mixture.
okay, how would it be heterogeneous? then?
If it's heterogeneous, then that's like trail mix, right? So they have,
Okay.
usually for compounds, it's not, thanks you too, thanks for coming. It's a little bit harder to find heterogeneous mixtures. Think of that more as like an alloy, right?
Okay.
They have some metal ions and then it's mixed in periodically with other smaller metal ions.
Okay.
But in this case, when it's a compound or something like that, then it's still gonna, and it's just that compound, and then it
And
would
it's-
be
okay.
a pure substance. Yep.
Okay, and then also for this one, okay, so H and S, so with that, is hydrogen a non-metal or like, how is that, like, what?
Yes, so
Yeah.
hydrogen is considered, right, if you look at this color, it's a really
Yeah.
good one. Even though it sits on the
Mhm.
first group, it is considered a non-metal.
Okay.
So its bonds will always be covalent?
Its bonds will always
Okay,
be
okay.
covalent. Right, in your acids, they are still covalent compounds, but they have charges. So it's a polyatomic ion. So
Mhm.
the H plus and then your polyatomic ion for your acid, right? That's what creates an acid. Even though it acts,
So
it acts
basically,
like a metal in that case.
Every time we see H, we just think of it as covalent.
Pretty much, yep.
Okay.
Yep.
Okay, even though that it has like the +1 charge or,
Yeah, you can, hydrogen is that little finicky one that you can kind of,
There's an
like, it
exception.
should be on the right hand side
Yeah.
of the periodic table, but because it only has 1 electron, it has to sit
Yeah.
on that first
okay,
portion.
but then, or sorry, I'm not.
No,
question,
you-
no, no. So, but with sulfur, how would it, since like the +2 and the -2, since like the 2 came down there and it switched, I would think that'd be like ionic charges like switching, because covalent, you don't do that.
Yes, so if you, can you go back to your periodic
Yeah.
table?
Or there's a lot of tabs open.
Do you see this?
Oh my gosh, how did you
Um,
find anything?
I know what almost all of those are.
That's awesome.
So for this one, right, when you're looking at oxygen, sulfur is just underneath oxygen.
Mhm,
If you look at water, H2O,
mhm.
is that an ionic compound or a covalent compound? It's a covalent
Yeah,
compound.
we're covered.
Sulfur is just underneath it. So it's
Mhm.
doing the same thing,
Oh.
making the same bond as H2O. It's just
Mhm.
using sulfur instead of oxygen.
That's
Okay.
so weird. Okay. Okay, cool. And then I had a question not about that one.
Thank you.
Yeah, thank you. Thanks for coming.
This one, I'm confused. Is this, because the explanation,
The explanation does not give you, someone else
Okay.
asked me about this, does
yeah,
not give you the same explanation as like what the question is asking.
yeah, okay, so then I thought I was right.
Yes, so the empirical and the molecular formula for ethanol are different.
Mm-hmm,
This is false. When you look at ethanol, so this is methanol, right? The
Mhm.
CH3OH.
yeah,
This is ethanol.
mm-hmm,
This is also ethanol. If you were to combine however many carbons, how many oxygens, and
Yeah.
how many hydrogens you have, you get C2H6O.
okay,
Okay. This
mm-hmm,
stretched out version is not the molecular formula.
oh,
This is just a way for chemists to say this is the connectivity of your atom.
okay,
Right. So you're saying, okay, a carbon's bonded to a carbon, that's bonded to a oxygen.
okay,
Your molecular formula is just the simplest, or I'm sorry, the empirical formula is the simplest version of your molecular
of the
formula.
molecular, okay,
But this is the molecular formula, but it looks, if you were to combine it all, it looks like the empirical formula.
okay, yeah, because asking for ethanol, because I was confused, because I was like, okay, there's that, and then you put it all together, but they don't look exactly the same, I'm like, oh, so it's gotta be different, or, wait, it's not different, or, wait, are different, false, so they're the same.
They're the
Okay,
same.
yeah, I was
Yes.
like, okay, it's gotta be different, I'm like, this could be, I can go either way with
Yes.
this, I don't know which one.
Yep, so the molecular formula would be, it's if it looks like this,
Mm-hmm,
and then it was C4H12O2,
okay.
right? In that case, right, it's not C2H6O,
Yeah,
it's C4H12O2.
and that can be simplified.
And
to
that can be
empirical.
simplified to the empirical that
Okay.
matches ethanol. But this
Okay.
is the same as ethanol.
Super weird. Okay, okay, and then just refreshing my mind on what we said about the first one. H is always gonna be covalent, because our hydrogen is a non-metal.
Hydrogen is a
Is a
non-metal.
non-metal, and
Yep.
and covalent always shares the electrons.
Yes.
Okay, and then pure substance, since it's just NiS, not also with like H2O,
Mhm.
that's not like the mixture, it's just the pure substance.
It's just the pure substance, right? Anytime you just have a compound, it's a pure substance.
Okay.
Yep.
Thank you so much.
Yeah, you're so
Appreciate
welcome.
it.
I always like try to draw it back to water. I'm like, okay,
Yeah.
how does water work? And it's, yep, anytime. Are you getting a little bit better with everything?
Yes, it's just like, yeah, I'm not like as bad as I was, or it wasn't as bad as it was like